Okay, so welcome to the parallel session number 6, when we are going to talk about R in production, R world. We have 3 interesting talks today, so we'll have a bit more time, but in general it's 15 minutes per presentation. After that, we'll have a question and answer session at around 5 past 10. So please write in the chat session all your questions for the speakers, and at the end of the session we will invite all of them back to the stage to have this question and answer session. Okay, so our first presenter is Layik Hama. He is a software engineer at Leeds Institute for Data Analytics, and he is going to present powering Turing e-Atlas with R. So I invite him to this stage.
I can see myself. I assume you can hear me. So good morning, everyone. Thanks, Mirko. Thanks for the organizers. I should say good afternoon, good evening, wherever you are, but it is good morning here. So yes, I will be talking to you about powering Turing e-Atlas with R, and I think I should start by sharing my screen and turning my camera off. Find that, then I should be able to stop my screen. And I assume you can still see my screen, just to double check. I think that is fine. So here we are. I will be, first of all, introducing who I am, where I come from, and the team. So I am based at Leeds Institute for Data Analytics. As I was introduced, I am a software engineering graduate, but I did my PhD at Leeds, again, with a group who are still interested in virtual reality and visualization. Current project is with Dr. Nick Lomax and Roger Beecham, who are both at Geography, but associated with LIDA, or Leeds Institute for Data Analytics, and also I think at least Nick is a Turing Fellow. The theme is a part of urban analytics, where names like Sir Alan Wilson, who used to head Turing Institute. I'm not going to introduce the institute. I just have too little time. And Professor Mark Birkin, who heads LIDA, is a chair of the urban analytics theme. It was started in May 2019, and it will run until October. The only thing I wanted to say here is the project is actually an idea from Alan Wilson himself, and it's a much bigger project. But these are just baby steps, really. If there are going to be interested in funding it further, then it could go much bigger. At the moment, it is really more geovisualization than research engineering, but it could be the other way, or engineering research, really. So I will try to talk about various aspects of the project, not a technical dive, not a visualization dive, but I'll have to say, when you talk about data visualization, it means graphics, which means using either your CPU or the GPU. But it also means human-computer interaction, disciplines creeping in. It has to be everywhere. As one of the speakers yesterday said, it could be useless on your machine. And it has to be interactive. And there is great reading there if anybody is interested. But in that theoretical context, it is really the technology that I'm going to talk about. Now, I will also talk about what R should be doing, where it does what it does best, and a little bit, obviously, about the project. But that picture is actually a recent GPU which burned. I don't want to say anything further, but you will feel it. So what is an e-atlas? That is a question that we still don't have an answer for, really. We just see quite a lot of work going on around the world. On the left is a work done at UCL, but in partnership with LEADER. And the middle, it is an opportunities atlas, which was presented at IEEE back in Vancouver last year. And on the right is a cancer atlas. There's also another Australian project. So there are quite a lot of atlases appearing. But since we are in this pandemic, there are loads and loads of COVID similar user interfaces appearing here and there. So is it a feature extraction? Is it beautiful pictures? What I'm really interested in is data exploration, interrogation to draw insights from the data, and also the challenge is combining different data sets so that you can draw insights or extract features. And also it will ultimately be a decision-making tool, I hope, and one of public engagement as well. So when I was preparing the slides, actually, I wasn't sure that I was doing and preparing the right content for the right event, as this is the first time in e-Rum, and also not have had big interaction with our community. But as it was mentioned throughout yesterday, it's probably one of the two choices. When I started, I was more into Python than I did R. So there you are. But if open source is still a thing, and I was glad somebody mentioned it again yesterday. So both are open source tools, and that's what we are doing as well, pushing the code as we work on it and keeping it open and open to collaboration as well. So it is also worth mentioning that that grammar graphics and the excellent work like ggplot2, for example, or ggplot if you like, are really important matters when you consider your choices when it comes to such projects, and that really translates into a great set of tools, and you yourself would have better reasons for, and we heard quite a lot yesterday. So straight in, if we are talking about graphics, this is what I drew for you for this event. I considered it the base between obviously a native, if I can call it a programming language, R, and the web engine that has been basically growing crazy because of reasons that is not the subject of this talk. But we will end up either on the CPU or the GPU of the machine, and I thought this would be the way they are categorized, and then add Python in there just to see. We either go directly to the CPU or GPU, for example, in R via RGL, or as I discover, for example, Ray Shader, which I think goes via RGL, but we can check that. Or you can reroute and go around, for example, in via R Markdown, and in Python in notebooks, you go back to the browser, and the browser again is built on V8, for example, in Chrome, and it is C++, and likewise for I think the other engines as well. If we then basically just dissect a little bit more R, we can find more information about it if we are interested. The only two things I want to mention here is it is not interactive, just because the way it is built, and also it's not. And that interactivity matters, and I'll touch on it again in another slide, and is not as widely available as the browser, just because the browser is something else. So I will be talking about React, but I'm not going to introduce React. You can read about it. Alex from RCG, I think yesterday mentioned these packages such as Vue and Angular and others, which inevitably will evolve because of the way JavaScript has basically just taken over the world. The left image is when I basically just search Google Scholar and got those numbers out and show it to you. The right is one by Stack Overflow, so the one on the right is more accurate. But what I wanted to highlight here is HTML and CSS basically can do quite a lot. And literally, we are convening, we are running the whole conference on these technologies. They are that powerful. So then let's talk about our web applications. When I joined Leader and when we needed to run a web application, Shiny was, I think, the choice, and Robin will speak later this afternoon. We discussed other choices, and I found Plumber, basically, which is inspired by Python Flask, which I have had basic interactions or use of. And then for this talk, I basically sat down and I said, so let's have a look at the two choices. They both rely on a package called HTTP-UV, and HTTP-UV is built on libuv, or there are similar packages, but libuv is powering Node.js, and it was built by Joyent, and I was surprised to see it obviously used in HTTP-UV, which is basically powering both of these two important pieces of R. So we move from web applications straight to web mapping, because that's where geovisualization would happen. And I love this picture. Just a bit of history, but this is where we are. We've got so many libraries, so many packages to use that you would really need help with navigating around it. I'm not going to touch these. Anybody interested, hopefully, will be able to see these slides later. So the atlas itself looks something like this. And again, if you remember the slide about other atlases, it is similar. It does use what you see. The bars here are straight from the GPU, and I understand, I think the Mapbox tiles are also probably going through well, they are going the GPU, the vector tiles, and the sidebar is there for interaction. The whole data extraction, data exploration thing goes on in there. And I knew this would happen, so let me just refresh this particular page of the slides. It's all done on the web. So there we are. Just one of the functions that I thought I needed to add into a package called GeoPlumber, and again, I'm not going to waste your time on that, but that's where React and R meet, basically, thanks to Plumber, hence the name GeoPlumber. So we can do basically embedding a map, just like we do in many other great React. R packages like MapView, like MapDeck, and etc. So I just wanted to again, being at our conference, there has to be a snippet in there. The package GeoPlumber basically puts together what's good in R and what's good in React and JavaScript on the client side, basically. A simple snippet there for those of you who wish to discover the repo and get started with it later. And the idea is this, and I'll explore this in the next slide. R does not do the essential UI. R does what it does best. And should be at the moment the pipeline work, for example, for the web application. And then I think that is the sweet spot of decoupling. So the right image I got from, again, Alex's Shiny presentation yesterday. The left is a piece of code from GeoPlumber package, which is still not CRAN, should be. In both cases, we are mixing the two, R and JavaScript in my case, and HTML on the side. And this goes back way, and we've got a programming language called PHP, which is built on this, and it is the wrong choice. And PHP built the world. So it works. It has worked. It's just not the way we're doing things at the moment. And the reason is we will be doing everything on the browser, not talking to the server. We just ask for the data. We've got everything you said you wanted us to visualize. Now just keep sending the data, and the browser can do the rest. Sorry, I think we've got one more. So in the Turing Geovisualization Engine, or the Atlas, is more of an application itself, but also a front-end part, which at the moment is an NPM package released, and that has been brought back into GeoPlumber so we can explore data in it, and it would look like something like this: that you do your own R processing, and then in a function you would call the Atlas, and it would show you a similar interface, basically. And just to summarize, we've got data coming in as different files. We go through these powerful programming languages, and we end up with some visualization. And no doubt there's quite a lot that the machine can do, and we shouldn't be doing. And the slide itself is part of a data processing, basically theoretical framework, and this would be the extraction part of that process. And underneath, when it comes to finally in the front end to do the visualization on the, I'm not sure if I've got time left.
Yeah, Layik, you have 1 minute, please. Okay.
Thank you very much. Just looking at my clock here. This is what's happening, and we're not going to look at that. Anybody interested can find out. I just wanted to mention there are similar projects, for example, Microsoft's Sundance and Uber's own Kepler-GL, amazing work. And I try to bring these, and I will try to bring them into GeoPlumber package. And then you would touch on the world of visualization. Again, I'm not going to go in there. And there are COVID applications of this. I could show that, but I think I'm running out of time. And at the end, this is where we are. And I'll focus on the last bit. Send the instructions to the browser only once, and subsequently just wire the data. Let the browser do its work. And thank you very much.
Thank you, Layik. Thank you very much. So if you still have some questions for Layik, please write them on the chat, and at the end of the session we will have these questions and answer all together. Okay, so thank you very much. And the next speaker is Massimiliano. He's the head of Advanced Business Analytics in SDG Group, and he's going to present Dplyr Snowflake integration for cloud-based massive and fast data manipulation. So thank you, Massimiliano. The stage is yours.
Thank you. So good morning, everyone, and thanks for giving me the opportunity to have this chat, this intervention. I'll just briefly introduce my role, and I'm the head of the Advanced Business Analytics in SDG Group. That's a global consulting firm, and I'm passionate about deploying, delivering, designing advanced analytics architecture. So the name of the unit I'm leading is Advanced Business Analytics. And most of the times, this business unit there is the data science people. And I like to focus my intervention of kind of issues and kind of challenges I faced during the years. So about 10 years ago, we start having the objective of putting in production, setting in production some data science statistical models that are useful for companies. So that's really important for us also to have a focus on the business side of things. And most importantly, that the model that we're building with the R specifically would need to run within the decision time that is needed from the project, and to give customer the benefit of the model itself and the objective. I'll just briefly tell you a story about 10 years ago, one of the first model that we've been designing, and I remember the main objective of that project was to measure the impact of the investment that retail companies, high-level street fashion companies were putting all their money in the shop windows. They were rotating every 14 days worldwide. This company does have currently 400 stores worldwide that they were investing millions of euros or dollars in this case as well, in some cases, on shop windows. And the objective of this project was to measure it, to understand if that actual investment was worthwhile. And what we did is to build an excellent model that was trying to forecast different KPIs. So expected KPIs that were improving was the conversion rate. So we did expect more people to walk into the store and more people to buy something after they walk into the store. So that's the logic of the conversion rate. So, and also the sales of the product that are actually exposed in the windows was expecting to grow after the product itself was exposed in the window. So we did model 5 different KPIs that were forecasting the values before the window actually was exposed. And then all the differences between the forecast and the actual data were the actual impact. So if for a specific product, a specific shoe or bag that it was, there was a positive difference between the forecast and the actual, then that means the window was working. And that was perfect. So our main references were the business references. They were happy. It took some time to us to explain all the math on the statistics behind that model. And that was good. And then suddenly the customers say, okay, let's go in production.
Sorry, Massimiliano, can I interrupt you? Do you have slides? Because we are not...
Yeah, I will use a slide straight away after.
Okay, sorry, I was just...
No, not to worry. Not to worry. I just like to have this 5 minutes introduction. So we were happy to share this logic with the customer, and the customer was happy, was time consuming and things like that. But after we wanted to go in production, the problem was that this forecast was supposed to run every day because we wanted to measure the impact every day because they were rotating the windows and they're rotating the products. And then when we put that in production, this customer have 8 node, okay, Hadoop-based infrastructure, okay, and we deployed that in production. The problem was that this customer does have 400 stores, and each store was actually taking the model to execute was taking 1 hour. So we didn't have 400 hours per day. And that was when I said, okay, guys, we need to concentrate a bit more on what we are going to do in order to make it feasible. So we start investigating different technologies that would allow us to do a good model as it was, but also to have it in a production time. So I just ran quickly through another use cases, and now I'm using my slides. Okay. And this is the additional use case. Okay, it's called Acme. This is for a pharma company. Okay. So as all of us know, these are the 4 main project steps we go through: and data mapping, data preparation, discovery, model, and then there is the production, of course, that's the latest one. And the preparation and data discovery and map are really, really time consuming, okay? And within this project, the main objective was to understand and to identify the golden cycle for production. So we do have data coming from sensors. We do have 22 sensors installed in the production line. The cycle was lasting about 4 hours, and the production cycle was in 8 different phases. It's a washing and sterilization cycle. So the main objective was to identify and to cluster the different cycles, the different batch going to the cycle, and to cluster them in order to identify and cluster itself the footprint of the sensor. So basically, we needed to identify golden cycle. In order to do that, we analyzed the production cycle. We analyzed the cycle based on the sensor data with the data coming from the sensor. And we applied a cluster analysis on multivariate time series. what we use is a permutation distribution clustering, and the main focus of the attention is that it clusters the time series based on the shape rather than the scale.
Massimiliano, could you please turn off your camera? So because of the recording, I'm sorry, we need to have the screen full. So please turn off your camera, and then we can all see just your screen share.
Would you like me to stop my camera?
Yeah, it's just for the video recording. Thank you.
Okay, sorry. So, okay. So it clusters the time series based on shape rather than the scale. Okay, so basically, yeah, that's it. Okay. So for each cycle, we projected a time series. Then we perform the permutation, and in order to identify the different patterns, different shapes within over time, and we perform the permutation and we counted them. And then we use a metric to measure the distance between distribution. So more is closer, more is part of that cluster, more is distant, and probably there is another cluster. And then we identify, okay, the optimal number of clusters in order to being able to associate the single batch to a single cluster in order to identify the shape and how the cluster, how the different batches will go to that cluster. And the strength of this algorithm that we use is definitely efficient. It's robust. More importantly, it handles time series of different lengths because the duration of the cycle, of course, there is about 4 hours, but it's different. And it's invariant to differences in mean and variance of the time series. There is no need for normalization. So these are examples of data coming from sensors and the cycles. What we do, we perform the permutation distribution. So we actually trying to associate the shape, as I said before. And then here we identify 6 different clusters. That was the optimal number in order that we were able to associate the vast majority of the batches and the single sensor value when the batches go through the production line. So we are able to do so. This is a shiny kind of visualization we used in order to do that. So each single sensor, each time a batch goes through the production line, we do associate the sensor shape to the cluster that we identify based on the footprint in order to understand where are the main area of efficiency for the production, given the distance between the golden cycle. The golden cycle is the cycle that I have optimal one. So I just want to and that was the challenge, that was the objective. And the thing is that we needed to do this continuously. We are now currently putting production in different sites, different sensor, different production lines, different batches, and we need something that works in parallel very well. And we have a massive amount of data because this is a multinational company that does have more than 40 different manufacturing sites, and within a site there is also 22 production lines. So we need to scale a lot, and we need to put in production. So that's why we implemented an architecture that has at its core Snowflake. Why we did that? Because we were able to scale all the work in terms of data preparation and data manipulation at the start, because we get this rough data from the sensors, we need to clean it. And normally, if you don't have such a database underneath, and if you don't demand to the SQL-based database, then it's a main issue, because otherwise in all other projects before using such a technology, we always face the issues of how many CPUs, GPUs you have to associate to the cluster. We went to the other direction. So all the data are loaded in Snowflake. All the data preparation work before the model actually runs and executed is done on Snowflake in order to scale, and we load it. We load the data on Snowflake, We run all the preparation, and then interfaces between the model and the snowflake is run to Dplyr as the title of my intervention. That translate some R languages into SQL in order to perform this model within the existing architecture, not having, so we were managing to put all our statistical model that we designed within a proven architecture, the scale in minutes to SQL languages without need of intervening there. This is just an overview of the cycle. So basically what we do, as I said, is we load the data, is based on AWS, then we put the data in R and then do in Snowflake, all the preparation is done. And then there is the additional component that in this case is SageMaker that would allow to have as many processes in parallel as we want connecting to the data to Snowflake. And just to close up, so why we selected that? Because again, using Snowflake would allow you to give to the organization the ability to benefit of this model within a time frame that is good. You can parallelize all your model, you can execute them in parallel, and you actually able to not to ask the customer to install anything else. So here we are in a pharma industry, for example, and it's not easy to validate from GMP perspective any other components. So we have inserted this model, as I said, within AWS infrastructure with Snowflake underneath, executing the model in parallel. And I think that's it from my side. Okay.
Thank you. Thank you, Massimiliano.
Thank you.
Okay, so please, if you have any questions, please write them on the chat area, and at the end of the session, I will ask again. I will ask all the speakers again to join the session for the questions. So, thank you very much. And our next speaker will be Sarah Gibson. She's a research software engineer in the Alan Turing Institute. Going to talk about supporting R in the Binder community. Thank you, Sarah.
Hi, good morning, everybody from London, where it's very, very rainy. Thank you very much for having me. The thing I'm going to do is in the session chat, I'm going to share a link where my slides are available, just in case you'd like to follow along, or they're not very visible on your screen or anything like that. These slides are also published under CC BY license, so if you feel free to remix and reuse them in your own talks. Just please make sure that you use the correct citation. So now I will begin. Oh, I won't do that. I will share my screen and we will get started. So yeah, I'm going to be talking today about supporting R in the Binder community. But first of all, if you're not familiar, I'm just going to give a super quick overview of what Binder is. So Project Binder is a global community of data scientists and software engineers dedicated to reproducible research. And the mybinder.org service allows anyone to launch a complete interactive computing environment in the cloud by clicking a link in their browser. By complete, I mean code, packages, assets, prose, media, everything is available in your browser without any pesky installation. You literally just click a link and it's there. So this is what it looks like from a researcher perspective. I'll just quickly talk through this comic. Here we have Jane. She's written a paper based on her experiments, and she would like anyone to be able to reproduce, check, or improve her calculations. So she describes her experiments in a Gibson notebook, although it doesn't have to be a Gibson notebook. You can write scripts, and in fact, Binder supports the RStudio interface, so you can write RStudio. And she collects together the prose, the code, the visualizations, and any resources she might need, like source code, data, and media. She publishes all of this on a publicly hosted repository, such as GitHub, but other platforms are supported as well. And then she makes that binder, repository binder ready by describing the software required to run the notebook in a configuration file. Many of you will be R users. So in your case, if you're writing a package, the name and description files will configure this, or we have a special file called install.r, which uses mran and the list of the install.packages commands to pull the versions of your packages from that particular date of the mran snapshot of CRAN. Put all of this together, a version controls repository and description of the software dependencies, and now everyone around the world can run and reproduce her computations. So here's a little bit of the history of my binder. We were originally launched in 2015 by Jeremy Freeman, and the first joint meeting between Binder and Jupyter happened at the beginning of January 2017, and that was to help maintain and support the project. The first half of that was spent redeveloping the back end into what is now Binder Hub. And in September of 2017, Binder received a More Foundation proposal, funding opportunity as well. So since our humble beginnings, we've now grown to hosting over 140,000 user sessions per week. So in roughly 3 years, we've brought this tool from a prototype to a staple of the open science community. And one way we did that is by federating the service. So mybinder.org is supported by 4 clusters around the world, including one that I myself manage at the Turing Institute. And the federation allows us to be resilient against both cluster outages and funding streams. Sustainable by sharing the workload and knowledge, the service can persist in spite of changes among resources and people. And robust, we can reliably support users present and future. So Binder itself is open source and it's built on open source tools. And this means that anyone can deploy their own service in an institution and allow sharing between specific teams, which I represented here by changing the globe for a little house. Or indeed, they can apply to join the federation and continue to support our broad user base. So what open source tools do we use under the hood? This is a quick diagram of what happens when you between clicking launch on the mybinder.org page and your browser being redirected. We use Git to clone repositories. We have a specialized tool called repo to Docker that builds a Docker image from the software described in the repository. We use Docker to execute these images. And then we have a Jupyter Hub running underneath that provides a connection between the running Docker container and the computational resources. In this case, our resources are Kubernetes clusters in the cloud. And then Binder itself is a thin layer on top of all of these tools that redirects the user's browser to the running Jupyter server in the container, which Jupyter Hub has made available. So the Turing's collaboration with Binder comes under our new Tools, Practices and Systems research program. And this represents the work that needs to be done for research in all domains to progress reliably and responsibly. It has some rules of the game that the program aims to embed so that the outcomes can be beneficial for everyone. I've highlighted 2 rules that the collaboration between the Turing and Binder particularly represents. Specifically relevant to this talk is leadership in open research. Binder is very passionate that we do not forge a path ourselves, but instead listen to our communities, meet them where they are, and help implement the features they'd find most useful. And this is why I'm giving this talk today. So a little bit of background. This year, I've been awarded a fellowship from the Software Sustainability Institute. The SSI facilitates the advancement of software in research by cultivating better, more sustainable research software to enable this world-class research. The fellowship program provides funding for researchers who want to improve how research software is used in their domains and/or areas of work. Since Project Binder is already doing so much to support reproducible research by facilitating these shareable, reproducible computational environments, I decided to use my fellowship to help nurture the Binder community. As with any open source project, Binder is not perfect and we face our own issues. So despite Jupyter standing for Julia, Python, and R, the development team are very Python-centric. So 2/3 of our name-supported community are not well represented among the team. This makes it tricky to help users with those languages or develop Binder into that space. We also have quite a small number of active maintainers. So this can like slow down development, and this is the impact that a small buzz factor can have on a project. So let me give an example of how this is relevant to folks on the call. My binder.org team regularly run a user survey to assess how the service is being used and also how users are finding the experience. When asked if you could change one thing about Binder, what would it be? This is one response pertinent to the R community. It says, if it was possible to have the pre-built images launch faster, that would be awesome. It's one barrier I have convincing my R friends to try Binder instead of Shiny apps. I want to start by giving a shout out to two already community-driven projects that are already doing a lot to support our users using Binder. These are Rocker, which compiles Docker files with different R setups, and Hole Punch, which automatically generates Binder configuration files for your project. These projects are already going a long way to helping our user base. But part of this problem with the slow to launch thing is that we are reliant on upstream contributions to other open source projects to speed up our launches. For example, pulling images with Docker onto our clusters or allocating computational resources with Kubernetes. The other half of how we solve this problem is how do we build the images in the first place? We have developed a Conda solution to installing R that meant it no longer required to be built from source on Linux. However, this isn't a common way of installing R in the community. There aren't any binaries available for Linux distributions, which Binder uses, which is why the builds can be so slow. And there doesn't seem to be interest in the community to create and maintain them. So far, Conda Forge are the only ones. But maybe the RNVAP package is the next thing we should implement, and we need guidance from the community here. We'd like to learn more about how RNV works under the hood. If it uses CRAN or something else, that could be the key to unlocking a more satisfactory experience for the R community. So I've just been really cheeky and asked you all to help out with Binder. So what do you get out of it? Well, it's an opportunity for the R community to shape how Binder moves forwards. We can work together to improve and provide support for the features that are most useful to you. And hopefully you'll get the thing that I'm most grateful for, which is being part of, well, another very welcoming and supportive community. So if anybody is at all interested in getting in touch and finding out more, here are a whole load of links of how you can do that. And my email is at the top if you'd like to reach out directly. Thank you very much.
Thank you, Sarah. Thank you very much. So now it's time for questions and answers. So I ask Sarah to stay, and please, Layik and Massimiliano, can you join us? Okay, we are losing, but okay. In the meantime, I can start with you, Sarah, because we received some questions here. Question 1 by Jeremy Selva. Can I use a Bitbucket repository that uses Git for version control instead?
Yes, we support Bitbucket, GitLab, GitHub, Zenodo, Dataverse, DOIs, Figshare, a whole range. If you go to mybinder.org, you'll see it where it says enter your URL. There is then a little drop-down menu, and that will give you all of the options you have. And you can even use just a bare Git instantiated repository as well, and gists. Okay.
So second question also for you, Sarah. So why Binder or Binder, sorry for the pronunciation, Binder. Why Binder is better than Google Colab, for example?
Binder is open source, which means we listen to our community, whereas Google is closed source, which means you may not see the features that you want deployed in Google Colab. And this is exactly what this talk is about. Come and tell me what you want. Come and tell me what Google Colab doesn't give for you, and we'll try and implement it in Binder.
Great. If you have comments about the questions, please also write them on the chat, and if we have some time, we can make an explanation better or any further questions. So for Massimiliano, from Peter Karcher, in order to get an idea of the magnitude of the problem, do you have some numbers concerning how many time series you have to process per day, per hour, and how long these time series are?
Yeah, sure. So as said, these numbers I'm giving you are just for pilot, and that is for one single production line. So they are multiplied by 5 after the production, we went into production. So the series are one number per second, okay, one data per second, okay, and they last for 4 hours. So we got about 14,000 points for each series. And series are about 3 or 4 per day. So we got about 1,500 series per year per production line. And we are, as said, this is just for the piloting for one production line. And then we multiply by 5. So we got about 7,500 series that we processed that. But it can scale because there is no limitation of the number of parallelism you can perform in the architecture described.
So I stay with you, Massimiliano, because Andrea Doll asked, regarding the Shiny dashboard, did you use the same database you used to run the model, or did you set up a separate database?
That's the beauty of using such a database like Snowflake. Because we didn't want and didn't need to separate them. And exactly that, and that's the same database where we do a visualization with Shiny, and we do a visualization with other visualization tools they do have the customer. So that's the beauty of the point. So we integrate the data straight away with the pipeline there, and then it can be straight visualized with Shiny or any other tools. Because you can scale up and down through an SQL command, it's a matter of milliseconds. The computing power you got available with the data. Okay. And we selected, AWS, but it's available on Azure and Google in some regions as well.
Okay, right, thank you. Sarah, Mark Hanley asked, what's the typical pathway to federation? How can we encourage our institutions?
Well, there isn't a typical pathway as of yet. And the Turing Institute is the only other, well, no, that's not true, because there's also GISIS, the social sciences, but we've both come at it from a very different way. So, for example, my pathway was I got involved directly with Binder and operating my binder.org, and I did this through the Turing Way project as well, which was advocating for reproducible research at the time. And then because the Turing Institute is already very invested in open infrastructure and producing tools that are open and like help other people do their research and stuff, it wasn't too difficult to put together a funding request to get cloud credits in order to set this up. And then as a member of the operating team, those discussions to introduce the Turing cluster into the federation were quite simple. If you're in an institution that is not as open as the Turing Institute is, I imagine that'll be a lot more difficult. We really need, it needs to be driven by a desire to uphold reproducible research and communication of research beyond just the closed silos that we currently work in, because that's what slows research down, is when we work in our silos and don't talk to one another. But that's just my experience as well. There's folks at GISIS and OVH who have different pathways as well. But we are very happy if you wanted to come along and ask on our repo, we would work out what would be the best pathway for you.
Thank you, Sarah. So we have one more question for you, in this time from Bikram Prakash. So can we use Plumber files in Rocker?
I can't answer that. I'm actually not an R user, I'm a Python user. The whole point of that talk. So I don't know anything about Rocker. I would advise going and checking out their repo.
Yeah. And I think we have one more for Massimiliano. Yes. is a question by Reyes Katie. So what's your view on best technologies for deploying Shiny apps outside our server, for example, Amazon Web Services, Apache, etc.?
Right. From again, from my perspective, there is no best technology overall. Depends on what your requirements are. There is no best ever technology for everything. Considering that for us, it's really important to have everything integrated in one point. So in this case, for our platform, we decided AWS. So definitely, if your question is what is the best technology for deploying Shiny app in the context I described, I would say AWS. Okay. Of course, depending on what is the objective. If the use case was different, then of course we selected AWS as a platform for the Snowflake interface, for security, for additional services, and SageMaker works really well. So it's the combination of the three together reason. It's not just best out of the box.
Layik, please, you had something to add.
Yeah, so no questions for me, but Rocker, I understand if it is the Docker image with R, you just install Plumber. It's just a package. Feel free to even try GeoPlumber. So yes, it literally, they're compatible.
I saw that Atlas is based from GeoPlumber, right?
Sorry, what was that?
The e-Atlas is actually
yes,
a GeoPlumber.
So the e-Atlas is powered by the not released package called GeoPlumber. So it's a GeoPlumber instance. And the technicalities is just too much to get into, really. The repo is there, and those interested can find out. But it's just an introduction to today, really. There's so much more to go around about it. There's the Docker file. They can, it's a self-contained instance. For example, I didn't have time, but the geoplumber.com currently showcases a COVID application that is a one instance Docker file. You don't do anything else. You just run the Docker image, and the whole thing is self-contained in there. Yet there are still those technical details that I presented in.
No, I saw that well, Sarah is a Python user. Layik, also you mentioned that you would have preferred to start with Python on this project.
You do what you're familiar with. You can't blame people for picking what they're familiar with. It is a brave decision to cross. And I was asked that question: would you be willing? And I knew something about R. The R people are smart people. That is nothing to be really either. I don't want to say this, or it's self. The academics, they're smart people, Professor Rossi Haka and everybody else, and they're smart people. Yes, Python developers are developers, and they power the world. But our users are statisticians, and they're smart people.
Do you have any questions for each other? Maybe now is a chance.
No, I might actually try my binder, and it's lovely to hear from Sarah and again, Massimiliano. But yeah, if they've got a question for me, I don't.
Okay. Anything else that you would like to add before we wrap up this session?
Thank you very much for having me. Thank you. Amazing effort.
Yeah, thank you.
Thank you.
Okay, so thank you, everyone. You will still have the chance to contact our presenters later during in the chats or in Slack, or just Google them. You can find them on the internet. So thank you, Sarah. Thank you, Massimiliano. Thank you, Layik, for presenting today. See you around.
Thank you.
Thank you. Bye.
Bye-bye.
Bye.
Bye. Thank you.